Close your eyes and imagine holding your smartphone. Feel its weight in your palm. That small, rectangular device contains one of the most extraordinary journeys on Earth. The lithium inside your phone has traveled over 10,000 miles, survived explosions, endured temperatures that would melt copper, and passed through the hands of miners working in some of the most remote places on our planet. Tonight, we'll follow that incredible journey together, from the ancient salt flats of Chile's Atacama Desert, where flamingos once danced beside pristine lagoons, to the bustling factories of China, where millions of battery cells are born each day. We'll discover the hidden costs, the remarkable innovations, and the human stories behind the small miracle that powers your digital life. This is the secret life of your smartphone battery, a story of chemistry and geography, of human ingenuity and environmental consequence, of ancient geological processes and cutting-edge technology. Let this journey carry you gently into sleep as we explore one of the most complex supply chains ever created by humanity. Our story begins in a place that seems almost alien to our modern world. The Atacama Desert in northern Chile stretches endlessly under a sky so clear that the world's most powerful telescopes gather here to peer into the cosmos. This is the driest, non-polar desert on Earth, where some weather stations have never recorded rainfall. But beneath this seemingly lifeless landscape lies a treasure more valuable than gold in our digital age. Deep underground, in vast salt flats called salars, lies lithium, the lightest metal on Earth. Born in the hearts of dying stars billions of years ago, the Salar de Atacama is a geological marvel. Imagine a vast white plain stretching to the horizon like a frozen sea. This salt flat covers over 1,200 square miles, larger than the state of Rhode Island. For millions of years, ancient lakes evaporated here, leaving behind layers of salt and precious minerals. The lithium settled deep below, concentrated in underground pools of brine that are more valuable than any pirate's treasure. The indigenous Licananti people have lived here for over 1,000 years. They call the water cycle pori, a sacred connection between earth and sky that sustains all life in this harsh environment. For them, water is not just a resource. It's the spiritual foundation of their existence, connecting them to their ancestors and the cosmos above. But in the 1980s, everything changed. Mining companies discovered that this remote desert contained nearly half of the world's lithium reserves. Today, massive pumps work around the clock, extracting over 63 billion liters of brine each year. That's nearly 2,000 liters every single second, enough to fill an Olympic swimming pool every 20 minutes. The extraction process is both simple and profound. Workers drill deep into the earth, sometimes 400 feet down, to reach the lithium-rich brine. This ancient water, older than human civilization, is pumped to the surface and spread across enormous evaporation ponds that stretch across the desert, like geometric lakes of turquoise and emerald. Under the relentless Atacama sun, the water slowly evaporates over 12 to 18 months. The brine becomes more concentrated, changing colors as different minerals crystallize and settle. First, common salt precipitates out, then potassium. Finally, the precious lithium carbonate remains white crystals that will eventually power your phone, your laptop, and millions of electric vehicles around the world. But this process comes with a hidden cost that's only now being understood. In 2024, scientists at the University of Chile made a disturbing discovery. Using satellite imagery and ground measurements, they found that the Atacama Salt Flat is literally sinking. The land is subsiding at a rate of 1 to 2 centimeters per year, nearly an inch annually, as the underground water is depleted. Castillo, the young researcher who led this study, describes it as a slow-motion catastrophe. As the groundwater disappears, the soil compacts and becomes less porous. When rare rains do come to the desert, less water can be absorbed into the ground. The land is losing its ability to store the precious water that sustains the delicate ecosystem of this harsh environment. The environmental impact extends far beyond the mining sites. The Atacama Desert, despite its apparent barrenness, supports a remarkable web of life. Underground springs feed lagoons, where 3 species of flamingos, Chilean, Andean, and James's flamingos, gather in pink clouds that can be seen from space. These birds have evolved over millions of years to thrive in this extreme environment, filtering algae and small crustaceans from the salty waters. But the flamingo populations are declining. The lagoons are shrinking. Sarah Plaza, a 72-year-old resident of the village of Pine, remembers when her community could swim in the wetland at Tilapozo. It was our oasis, she recalls. Our animals drank there. Our children played there. Today, that wetland is completely dry, drained by pumps installed in the early 1980s. The Licananti communities are watching their world disappear. In the village of Sacer, nearly every house displays a black flag symbol of mourning for their dying landscape and resistance to the changes imposed without their consent. Jeanette Cruz, a local teacher, explains that these flags represent their opposition to agreements made without their involvement, to a future decided by others. For many indigenous residents, the fear is existential. We could very easily disappear, says Sergio Cubelos, a native of Pine. Their culture, their spiritual connection to the land, their traditional ways of life, all are threatened by the insatiable global demand for lithium. Yet the mining continues to expand. In 2024, Chile announced its national lithium strategy, aiming to increase production by 70% within a decade. 26 new salt flats have been designated for exploitation. The government promises sustainable development, but critics worry that the focus has shifted primarily to profit, with environmental and social impacts being denied or minimized. This is where your phone's journey begins, in this ancient desert, in this complex intersection of geological wonder, environmental destruction, and human need. Every lithium atom in your battery carries with it the story of the Atacama, the dreams of the Licanante people, and the weight of our technological choices. As we leave the high desert and follow the lithium on its journey, remember that this is just the beginning. The white crystals harvested from these evaporation ponds will travel thousands of miles, through multiple countries and countless hands, before they reach the device in your pocket. While lithium provides the foundation of your battery, another element gives it power and longevity. Cobalt, a silvery blue metal that makes up about 12% of your phone's battery, has a story far darker than the pristine salt flats of Chile. Our journey now takes us to the heart of Africa, to the Democratic Republic of Congo, a nation that holds over half of the world's cobalt reserves. Here, in the Copperbelt provinces of Haut-Katanga and Lualaba, lies a tragedy hidden within every smartphone, every laptop, every electric vehicle on Earth. The DRC is one of the poorest countries on Earth, despite sitting atop some of the world's most valuable mineral deposits. over 73% of its population lives below the international poverty line. In this context of desperate poverty, an estimated 40,000 children work in cobalt mines as young as 7 years old. Let me tell you about Muntosh. He's 12 years old now, but his story begins when he was just 6. He watched his older brother die in a landslide at a cobalt mine, buried under tons of earth that collapsed without warning. Today, Muntosh works in the same dangerous tunnels, digging with his bare hands for cobalt, or that will eventually power devices around the world. These children work in what are called artisanal mine small-scale operations that are often little more than holes in the ground. They dig tunnels by hand, sometimes 40 feet deep, with no safety equipment, no protective gear, no engineering oversight. The tunnels can collapse at any moment. The air is thick with cobalt dust that burns their lungs and causes chronic respiratory problems. Faustin is 11 years old. He carries heavy sacks of cobalt ore on his back, sometimes weighing more than he does. He works 12-hour days for less than $2. He should be in school, learning to read and write, playing with friends. Instead, he's falling further behind academically with each passing day. "I regret missing school," he says quietly. "I see my friends surpassing me, and I know I can never catch up." The children are exposed to toxic materials every day. Cobalt dust causes asthma and chronic bronchitis. Heavy metals in the OR can damage developing brains and nervous systems. Many children suffer spinal deformities from carrying loads too heavy for their growing bodies. Injuries from collapsing tunnels, unsafe equipment, and rudimentary tools are common, often resulting in permanent disabilities. But perhaps the deepest wounds are psychological. These children experience anxiety, trauma, and emotional distress from the exploitative conditions. They witness accidents, lose family members in mining collapses, and live without the stable childhood environment that every child deserves. The mental health impacts will follow them for the rest of their lives. The root cause of this tragedy is poverty so extreme it's difficult for those of us in wealthy countries to comprehend. Rising living costs and widespread hunger affect an estimated 25.4 million people in the DRC, 1/4 of the entire population. Families rely on their children's income for essential needs like food and shelter. Education, while theoretically free, requires informal fees that are prohibitively expensive for most families. Conflict and natural disasters have disrupted education for 2.7 million children, leading to the closure of 848 schools. Children over 12 are not legally required to attend school, making them vulnerable to labor exploitation. Female minors, lacking childcare options, frequently bring their children to work. What begins as necessity becomes normalization. Children grow up believing that dangerous mining work is their only option, their only path to survival. But there are people fighting to change this story. Organizations like Save the Children have created catch-up clubs, accelerated learning programs that help child miners reintegrate into schools. These programs provide not just education, but financial stipends for families and socio-emotional support for traumatized children. The International Labor Organization launched the Gallup Project in 2024, building on previous efforts to strengthen remediation services for children identified in mining operations. Their ultimate goal is ambitious but necessary: 0 children in the mining sector. The African Development Bank's Pabia Cobalt project has successfully removed over 9,000 children from artisanal cobalt mines and reintegrated them into schools or vocational training programs. They address not just the symptoms, but the root causes: extreme household poverty and inadequate social infrastructure. Progress is being made, but it's slow and difficult. The child labor monitoring and remediation system has registered over 6,200 children working in mines in just 2 provinces. Each number represents a child whose childhood has been stolen, whose future has been compromised by our global demand for the metals that power our digital lives. Companies are beginning to take responsibility. Some are implementing due diligence programs to trace their cobalt supply chains. Others are investing in community development projects, building schools, and providing alternative livelihoods for mining families. But the fundamental challenge remains. As long as there is desperate poverty in the DRC, and as long as there is global demand for cobalt, children will be at risk. Every smartphone, every electric vehicle, every renewable energy system that uses cobalt-containing batteries carries with it the moral weight of this crisis. The cobalt in your phone has likely passed through these mines, through the hands of these children. As consumers, as citizens, as human beings, we have the power to demand better. We can support companies that prioritize ethical sourcing. We can advocate for stronger regulations. We can invest in technologies that reduce our dependence on conflict minerals. The children of the DRC deserve better than a life spent digging in dangerous tunnels for metals that power our convenience. They deserve education, healthcare, safety, and hope. Their dreams matter as much as our technological progress. As we continue our journey, following the cobalt from these mines to the factories where it will be transformed into battery components. Remember Muntosh and Faustin and the thousands of other children whose lives are intertwined with the device in your pocket. Their stories are part of your phone's story, part of our shared human story. The path toward ethical technology is long and complex, but it begins with awareness. Our journey now takes us to the manufacturing heart of the modern world. The lithium from Chile's desert and the cobalt from Congo's mines converge in the vast industrial cities of China, where they undergo an almost alchemical transformation from raw earth into the sophisticated energy storage devices that power our digital lives. China produces more batteries than the rest of the world combined. In 2024, Chinese factories have the capacity to meet the entire global demand for batteries, a manufacturing capability so vast it has created a global oversupply. This dominance didn't happen overnight. It's the result of decades of strategic investment, technological innovation, and an industrial ecosystem unlike anywhere else on Earth. Let's follow our materials as they arrive at one of China's massive battery manufacturing complexes. Picture a facility the size of several football fields, where millions of battery cells are born each day. The air hums with the sound of precision machinery, robotic arms moving in perfect synchronization, and the quiet efficiency of automated production lines that never sleep. The lithium carbonate from Chile arrives as white powder, pure as snow. The cobalt from the DRC comes as refined metal, its dark history transformed into gleaming industrial input. These materials, along with nickel, manganese, and other elements, begin their transformation in massive mixing chambers, where chemistry becomes art. The first step is creating the cathode positive terminal of your battery. Engineers blend the lithium, cobalt, nickel, and manganese in precise ratios, creating what's called a cathode active material. This powder is mixed with binding agents and conductive additives, then coated onto thin sheets of aluminum foil in layers thinner than human hair. The precision required is extraordinary. The coating must be perfectly uniform across miles of foil, with no gaps, no bubbles, no imperfections. Even a microscopic flaw can cause a battery to fail, overheat, or worse. Quality control systems use lasers and cameras to inspect every inch of material, rejecting anything that doesn't meet exacting standards. Meanwhile, the anode negative terminal is being prepared, traditionally made from graphite. Some manufacturers are now experimenting with silicon additives that can dramatically increase battery capacity. The graphite is processed into a fine powder, mixed with binders, and coated onto copper foil with the same meticulous precision as the cathode. Between these two electrodes lies the separator, a thin plastic membrane that keeps the positive and negative sides apart while allowing lithium ions to pass through. This separator is one of the most critical safety components in your battery. It must be strong enough to prevent short circuits, yet porous enough to allow efficient ion flow. The assembly process is a marvel of precision engineering. In clean rooms that rival those used for computer chip manufacturing, robotic systems stack the cathode, separator, and anode in precise layers. Some batteries use a jelly roll design, where long strips are wound together like a Swiss roll. Others use flat, stacked layers like pages in a book. Each cell is then placed in its housing, usually a thin aluminum pouch or a cylindrical metal case. The electrolyte, a carefully formulated liquid that allows lithium ions to move between the electrodes, is injected into the cell. This electrolyte is like the blood of the battery, carrying the electrical charge that will power your phone. The formation process comes next, the first charging and discharging of the battery. This initial cycling activates the chemical processes that will define the battery's performance for its entire life. Computers monitor each cell's voltage, capacity, and internal resistance, sorting them into quality grades. Only the best cells will make it into premium smartphones. Chinese manufacturers have perfected this process through decades of refinement. Companies like CATL, BYD, and ATL have become global leaders, not just in volume, but in innovation. They're developing new chemistries that charge faster, last longer, and operate safely in extreme conditions. In 2024, Chinese companies are pushing the boundaries of what's possible. They're working on batteries that can charge from 10% to 80% in just 10 minutes. They're redeveloping cells with capacities exceeding 6,000 million powers, enough to power a smartphone for days on a single charge. They're experimenting with solid-state electrolytes that could eliminate the fire risk of current batteries entirely. The scale of this innovation is breathtaking. Chinese battery manufacturers invested over 45% more in research and development in 2023 compared to the previous year. Government regulations now require companies to allocate at least 3% of their revenue to technological advancement. This isn't just manufacturing, it's a technological revolution happening in real time. But this industrial miracle comes with its own environmental costs. The factories consume enormous amounts of energy, much of it still generated from coal. The manufacturing process produces chemical waste that must be carefully managed. The sheer scale of production means that even small inefficiencies are multiplied millions of times over. Chinese manufacturers are increasingly aware of these challenges. Many are investing in renewable energy to power their factories. They're developing closed-loop recycling systems that can recover and reuse materials from old batteries. They're working to eliminate toxic solvents and reduce water consumption in their processes. The workers in these factories are part of this story too. Millions of people, mostly young migrants from rural areas, have found employment in China's battery industry. They work in shifts around the clock, their skilled hands and trained eyes ensuring that each battery meets the exacting standards required for modern electronics. These workers undergo extensive training to handle the sophisticated equipment and hazardous materials involved in battery production. They wear protective equipment, work in climate-controlled environments, and follow strict safety protocols. Their expertise and dedication are essential to the quality and reliability of the batteries that power our world. As your phone's battery nears completion, it undergoes final testing and quality assurance. Each cell is charged and discharged multiple times to verify its performance. Its capacity, voltage, and internal resistance are measured and recorded. Only batteries that meet strict specifications will be approved for shipment. The completed battery cells are then packaged for their final journey. They're carefully cushioned, labeled with tracking codes, and loaded into shipping containers for transport around the world. Some will go to smartphone manufacturers in South Korea, others to laptop makers in Taiwan, and still others to electric vehicle plants in Europe and America. The transformation is complete. The ancient lithium from Chile's desert and the cobalt from Congo's mines have become sophisticated energy storage devices, ready to power the digital revolution. But their journey isn't over. They still must travel thousands of miles to reach the factories where they will be integrated into the smartphones, laptops, and other devices that define modern life. This manufacturing process, repeated millions of times each day across hundreds of factories, represents one of the most complex and sophisticated industrial operations in human history. It's a testament to human ingenuity, to our ability to transform raw materials into technologies that would seem like magic to previous generations. Yet, as we've seen, this technological miracle is built on a foundation of environmental and social costs that we're only beginning to understand. The challenge for the future is to maintain this incredible capability while addressing the ethical and environmental challenges that come with it. As we continue our journey, following these batteries to their final destinations, remember the millions of workers, the countless hours of research and development, and the incredible precision required to create the small miracle that powers your digital life. To truly appreciate the battery in your current smartphone, we need to travel back in time. Close your eyes and imagine the year 1987. The Berlin Wall still stands. The internet is just a research project, and mobile phones are the size of bricks, weighing over 2 pounds and costing more than a car. The Motorola Dynatac 8.00.x, one of the first commercially available mobile phones, came with a battery that provided just 30 minutes of talk time and took 10 hours to charge. This battery was a nickel-cadmium cell, a technology that was revolutionary for its time, but primitive by today's standards. Users carried spare batteries and car chargers, planning their calls around their phones' limited endurance. The 1990s brought us the Nokia era. The Nokia 1011, released in 1992, could operate for up to 90 minutes on a single charge, a threefold improvement that felt miraculous to users accustomed to the limitations of earlier devices. Nokia's engineers were masters of power efficiency, squeezing every possible minute from nickel hydride batteries that were gradually replacing the older nickel-cadmium technology. But even these improvements seem quaint by today's standards. The Nokia 3310, beloved for its durability and week-long battery life, had a 900 mAh battery, less than 1/5 the capacity of a modern smartphone. Yet it lasted so long because the phone did so little. It could make calls, send text messages, and play Snake. No internet, no apps, no higher resolution display consuming power every second. The real revolution began in 1991, not in a phone factory, but in a Sony laboratory in Japan. Akira Yoshino and his team commercialized the first lithium-ion battery, a technology that would eventually power everything from laptops to electric vehicles to the International Space Station. Lithium-ion batteries offered something that seemed impossible. They were lighter than previous technologies, held more energy, and didn't suffer from the memory effect that plagued earlier rechargeable batteries. You could charge them partially without damaging their long-term capacity. They could be made in almost any shape or size. They were the perfect power source for the mobile revolution that was about to transform human civilization. The first smartphones to use lithium-ion batteries appeared in the late 1990s and early 2000s. The IBM Simon Ostin, often considered the first true smartphone, had a battery life measured in hours, not days. But it could send emails, browse primitive web pages, and run simple applications. Users were willing to trade battery life for capability, beginning a trend that continues today. The introduction of the iPhone in 2007 marked a turning point in battery technology and user expectations. Steve Jobs and his team at Apple faced an enormous challenge: how to power a device with a large, bright, touchscreen wireless connectivity and the processing power of a computer, all while keeping it thin enough to fit in a pocket. The original iPhone had a 1,150 mAh lithium-ion battery, modest by today's standards, but revolutionary for its time. Apple's engineers worked closely with battery manufacturers to develop cells that were thinner, more energy-dense, and safer than anything previously available. They pioneered new battery management systems that could monitor and optimize power consumption in real time. But the real breakthrough wasn't just in the battery itself, was in how the entire device was designed around power efficiency. Every component, from the processor to the display to the wireless radios, was optimized to minimize energy consumption. Software algorithms learned user patterns and adjusted performance accordingly. The result was a device that could last a full day, despite doing things that would have been impossible just a few years earlier. The smartphone revolution drove rapid advancement in battery technology. Manufacturers competed not just on features and design, but on battery life. Each new generation of phones demanded more from their batteries: brighter displays, faster processors, more wireless radios, better cameras, and increasingly sophisticated software. Battery manufacturers responded with innovations that seemed to defy physics. They developed new cathode materials that could store more lithium ions. They created thinner separators that allowed more active material in the same space. They improved electrolytes that could operate safely at higher voltages, increasing energy density. The evolution of smartphone batteries is also a story of changing user behavior. In the early days of mobile phones, users planned their communication around battery limitations. You charged your phone overnight and hoped it would last until evening. Calls were brief, text messages were precious, and the phone spent most of its time in standby mode. Today's smartphone users have completely different expectations. We expect our phones to be always on, always connected, always ready to capture a photo, stream a video, or navigate to an unknown destination. We use our phones for hours each day, often forgetting that we're carrying devices more powerful than the computers that sent humans to the moon. This shift in usage patterns has driven battery technology in new directions. Fast charging has become as important as capacity. Wireless charging has eliminated the need for cables. Battery management systems have become incredibly sophisticated, learning individual usage patterns and optimizing performance accordingly. Modern smartphones use batteries with capacities ranging from 3,000 to 5,000 million hours or more. But capacity alone doesn't tell the whole story. Today's batteries are also smarter, safer, and more durable than their predecessors. They can charge from 0% to 50% in 15 minutes. They can operate safely in extreme temperatures. They can last for years without significant degradation. The software that manages these batteries has become almost as important as the hardware itself. Modern smartphones use artificial intelligence to predict when you'll need power and when you won't. They can slow down background processes when the battery is low, reduce display brightness based on ambient light, and even learn which apps you use at different times of day to optimize power allocation. Battery health monitoring has become standard, with phones providing detailed information about battery condition and expected lifespan. Users can see how their charging habits affect battery longevity and adjust their behavior accordingly. Some phones even offer battery replacement programs, extending device lifespan and reducing electronic waste. The evolution of smartphone batteries reflects broader changes in how we think about energy and sustainability. Early mobile phones were designed to be replaced frequently with batteries that were difficult or impossible to replace. Today's phones are increasingly designed for longevity, with batteries that can be serviced and replaced, extending device lifespan. Manufacturers are also focusing on the environmental impact of battery production. They're investing in recycling programs that can recover valuable materials from old batteries. They're developing new chemistries that use more abundant and less environmentally problematic materials. They're working to reduce the carbon footprint of battery manufacturing. As we look toward the future, the evolution of smartphone batteries continues to accelerate. Researchers are working on solid-state batteries that could double energy density while eliminating fire risk. They're developing new materials that could enable batteries to charge in seconds rather than minutes. They're exploring wireless power transmission that could eliminate the need for charging altogether. But perhaps the most important evolution is in how we think about batteries and energy consumption. We're becoming more aware of the true costs of our digital lives, the environmental impact of mining, the human cost of manufacturing, the challenge of disposal and recycling. This awareness is driving demand for more sustainable, more ethical, and more efficient energy storage solutions. The battery in your current smartphone represents the culmination of decades of scientific research, engineering innovation, and manufacturing refinement. It's a testament to human ingenuity and our ability to solve complex technical challenges. But it's also a reminder of our responsibility to use technology wisely and sustainably. As we continue our journey into the future of battery technology, Remember that every improvement, every innovation, every breakthrough builds on the work of countless scientists, engineers, and workers around the world. The evolution of smartphone batteries is really the evolution of human knowledge and capability, one small step at a time. As you rest comfortably, let your mind drift forward in time. Imagine a world where your smartphone charges completely in just 10 minutes, lasts for days on a single charge, and never poses any risk of overheating or fire. This isn't science fiction, it's the promise of solid-state battery technology, and it's closer than you might think. The year 2025 marks a pivotal moment in battery technology. After decades of research and development, solid-state batteries are finally transitioning from laboratory curiosities to commercial reality. These revolutionary energy storage devices could transform not just our smartphones, but our entire relationship with portable power. To understand why solid-state batteries are so revolutionary, we need to look inside your current phone's battery right now. Lithium ions move between the positive and negative electrodes through a liquid electrolyte, essentially a chemical soup that conducts electricity. This liquid is flammable, can leak, and limits how tightly we can pack energy into a small space. Solid-state batteries replace this liquid with a solid material, often a ceramic or polymer, that can conduct lithium ions just as effectively, but without the safety risks. That's essentially what solid-state technology does for battery chemistry. The advantages are profound. Solid electrolytes are non-combustible, eliminating the fire risk that has plagued lithium-ion batteries. They're also less dense, allowing manufacturers to pack more energy into the same space. Early prototypes suggest solid-state batteries could offer double the energy density of current technology. Imagine your phone lasting 2 full days of heavy use on a single charge. But perhaps most remarkably, solid-state batteries can handle much higher charging currents without degradation. While your current phone might take an hour to charge fully, a solid-state battery could reach 80% capacity in just 10 minutes. Some researchers claim charging times of under 5 minutes are possible, though these claims remain to be proven in real-world conditions. The longevity improvements are equally impressive. Current lithium-ion batteries typically retain about 80% of their original capacity after 500 to 1,000 charge cycles. This could mean smartphone batteries that last the entire useful life of the device, perhaps 15 to 20 years. Companies around the world are racing to commercialize this technology. QuantumScape, backed by Volkswagen and Bill Gates, has developed a ceramic electrolyte that enables lithium metal anodes, the holy grail of battery technology. Solid-state batteries by 2027. Their initial designs promise 20% greater driving range for electric vehicles and charging times of 10 minutes or less. Toyota holds over 8,000 solid-state battery patents, many developed in partnership with Japanese petroleum company Idemitsu. In China, companies like SAIC and NIO are already offering semi-solid-state batteries in their electric vehicles, providing over 650 miles of range on a single charge. These represent an intermediate step toward fully solid-state technology, proving that the transition is already underway. The path to solid-state batteries hasn't been easy. For decades, researchers struggled with fundamental challenges that seemed almost insurmountable. The solid electrolytes had to conduct ions as efficiently as liquids, while remaining mechanically stable through thousands of charge cycles. The interfaces between solid materials had to be perfect, with no gaps or imperfections that could cause failure. One of the biggest challenges was preventing dendrite formation, microscopic, needle-like growths of lithium that can pierce through separators and cause dangerous short circuits. Researchers at the University of Oxford developed a multi-layered electrolyte design that deflects these dendrites at interfaces with varying stiffness, like a bulletproof vest for batteries. Harvard University scientists pioneered a composite anode approach using silicon particles that promote uniform lithium plating, eliminating dendrite formation entirely. Solid-state batteries require new production techniques, specialized equipment, and incredibly precise quality control. QuantumScape developed an innovative process called Cobra that enables cost-effective roll-to-roll production of ceramic. Electrolyte separators, a breakthrough that made their commercial timeline possible. Solid Power, another leading company in this space, received a U.S. Department of Energy grant to establish the first continuous production line for sulfide-based solid electrolytes. This represents a crucial step toward scaling production from laboratory quantities to industrial volumes. But solid-state batteries are just one part of the future energy storage landscape. Researchers are exploring even more exotic technologies that could revolutionize how we think about portable power. Sodium-ion batteries, which use abundant sodium instead of scarce lithium. Aluminum-air batteries could theoretically provide energy densities far exceeding any lithium-based technology, though they face significant technical challenges, though they currently can't store energy for extended periods. Perhaps most intriguingly, wireless power transmission could eventually eliminate the need for batteries altogether in some applications. Imagine smartphones that charge continuously from ambient radio waves, or devices that draw power from wireless charging fields embedded in furniture, vehicles, and public spaces. Research into wireless power has advanced significantly in recent years. Companies are developing systems that can transmit power over distances of several feet, potentially enabling truly wireless devices. While the technology is still in its early stages, it represents a fundamentally different approach to portable power. The future of battery technology is also increasingly focused on sustainability and environmental responsibility. Researchers are developing recycling processes that can recover 95% or more of valuable materials from old batteries. They're exploring bio-based materials that could replace some of the metals currently required for battery production. Closed-loop manufacturing systems could eventually eliminate waste entirely, with every component of old batteries being reused in new ones. This circular economy approach could dramatically reduce the environmental impact of our digital devices while ensuring a sustainable supply of critical materials. The human cost of battery production is also driving innovation toward more ethical supply chains. Companies are investing in technologies that could reduce or eliminate the need for cobalt, the metal associated with child labor in the Democratic Republic of Congo. Alternative chemistries using iron, manganese, or other abundant materials could provide similar performance without the ethical concerns. Blockchain technology is being used to create transparent supply chains that can track materials from mine to device, ensuring that consumers can make informed choices about the products they buy. This transparency could drive market demand for more ethical and sustainable battery technologies. As we look toward this future, it's important to remember that technological progress is not inevitably the result of human choice and effort. The breakthroughs in solid-state batteries, sustainable materials, and ethical supply chains are happening because researchers, engineers, and companies are choosing to prioritize these goals. The future of your smartphone's battery will be shaped by the decisions we make today about what kind of technology we want to support, what kind of world we want to live in, and what kind of legacy we want to leave for future generations. The solid-state batteries that may power your next smartphone represent more than just technological advancements. They represent hope for a more sustainable, more ethical, and more capable future. They are a reminder that human ingenuity can solve even the most complex challenges when we commit ourselves to the task. As we near the end of our journey through the secret life of your smartphone battery, remember that this story is still being written. The next chapter will be shaped by the choices we make, the technologies we support, and the future we choose to create. Every story has an ending, and every battery eventually reaches the end of its useful life. But in the world of modern technology, endings are often new beginnings. The final chapter of your smartphone battery's journey is perhaps the most important of all. Its transformation from electronic waste into the raw materials for future devices. Right now, as you listen to this story, millions of smartphones around the world are reaching the end of their lives. Their batteries, once capable of powering days of communication and entertainment, can no longer hold a charge. But these seemingly dead batteries contain a treasure trove of valuable materials: lithium, cobalt, nickel, and rare earth elements that took millions of years to form and thousands of miles to gather. The journey of battery recycling begins in your hands. When you decide to replace your smartphone, that old device embarks on a new adventure. In the best-case scenario, it's collected through a manufacturer take-back program or dropped off at a certified recycling facility. These programs have expanded dramatically in recent years, driven by both environmental regulations and the economic value of recovered materials. The European Union's battery regulation, implemented in 2023, requires that 65% of lithium-based battery weight must be recycled by 2025, increasing to 70% by 2030. By 2031, new batteries must contain at least 6% recycled lithium, 6% recycled nickel, and 16% recycled cobalt. These requirements are driving massive investment in recycling infrastructure and technology. At a modern battery recycling facility, your old smartphone undergoes a careful disassembly process. Trained technicians remove the battery, ensuring that any remaining charge is safely discharged. The battery is then sorted by chemistry type. Lithium-ion batteries require different processing than older nickel metal hydride or nickel cadmium cells. The recycling process itself is a marvel of modern chemistry and engineering. There are three main approaches, each with its own advantages and environmental implications. Pyrometallurgical recycling involves melting the entire battery at temperatures up to 1,450 degrees Celsius, hot enough to melt copper. This high-temperature process can recover metals like cobalt, nickel, and copper, but it's energy-intensive and cannot recover lithium or the plastic components. The process generates toxic gases that must be carefully controlled and treated. Hydrometallurgical recycling uses chemical solutions to dissolve and separate the different materials in a battery. This process is more complex, but can recover a wider range of materials, including lithium salts and plastic components. It's generally less energy-intensive than pyrometallurgy, and can achieve recovery rates of up to 90% for lithium-ion batteries. The most promising approach is direct recycling, which aims to recover battery components without breaking down their chemical structure. This method uses significantly less energy and can potentially recover materials in a form that can be directly reused in new batteries. While still in development, direct recycling could revolutionize the sustainability of battery production. Companies like Aqua Metals are developing closed-loop recycling systems that produce no waste streams. Their liquefining technology has an extremely low carbon footprint and avoids the sodium sulfate waste that traditional hydrometallurgical processes can produce, sometimes 1.5 to 2 tons of waste per ton of recycled material. The recovered materials from battery recycling are remarkably pure. The environmental benefits of battery recycling are profound. Using recycled materials can reduce carbon emissions by approximately 4 times compared to mining virgin materials. This reduction is crucial as the world transitions to electric vehicles and renewable energy systems that require massive amounts of battery storage. Recycling also reduces the pressure on mining operations. Experts suggest that effective battery recycling could contribute the equivalent of 30 new lithium mines to global supply by 2040. This could significantly reduce the estimated 273 additional mines that would otherwise be needed to meet projected demand. The recycling industry is also addressing the human costs of battery production by reducing demand for newly mined materials. Recycling can help decrease the pressure on mining communities, including the children working in cobalt mines in the Democratic Republic of Congo. While recycling alone cannot solve these problems, it's an important part of creating more ethical supply chains. The technology for battery recycling continues to advance rapidly. Researchers are developing new processes that can separate materials more efficiently, recover a wider range of components, and operate with lower environmental impact. Some facilities are experimenting with artificial intelligence to optimize sorting and processing, while others are exploring biotechnology approaches that use microorganisms to extract metals. The future of battery recycling looks increasingly sophisticated. Researchers are working on design for recycling approaches that would make batteries easier to disassemble and process at their end of life. This could involve using materials that are inherently more recyclable, designing batteries with fewer different materials, or creating modular designs that allow individual components to be easily replaced or recovered. Solid-state batteries, which we discussed earlier, may actually be easier to recycle than current lithium-ion technology. Their solid composition could make disassembly safer and more straightforward, while the higher value of lithium metal anodes could make recycling more economically attractive. But recycling is only part of the solution. The most sustainable battery is one that lasts as long as possible before needing replacement. This is driving innovation in battery management systems that can extend battery life. Software that optimizes charging patterns, and design approaches that make batteries replaceable rather than permanently integrated into devices. Some manufacturers are offering battery replacement programs that can extend device lifespan significantly. Apple, for example, can replace iPhone batteries for a fraction of the cost of a new device, keeping phones in use for years longer than would otherwise be possible. As consumers, we play a crucial role in this recycling ecosystem. Our choices about when to replace devices, how to dispose of old ones, and which manufacturers to support all influence the sustainability of the battery industry. By choosing devices designed for longevity, participating in take-back programs, and supporting companies with strong environmental commitments, we can help drive the transition to a more sustainable future. The concept of urban mining, recovering valuable materials from electronic waste, is becoming increasingly important. Cities contain vast quantities of valuable metals in their electronic waste streams, often in higher concentrations than natural ore deposits. Effective recycling can turn our cities into mines, reducing the need for traditional extraction. International cooperation is essential for effective battery recycling. Materials flow across borders throughout their life cycle, and recycling systems need to be coordinated globally to be effective. Organizations like the Global Battery Alliance are working to create standards and frameworks that can support sustainable battery value chains worldwide. The economic incentives for recycling continue to improve. The revenue generated per ton of recycled battery material is estimated to reach nearly $600 by 2025. This profitability is driving investment in recycling infrastructure and making the industry more attractive to both established companies and innovative startups. The story of battery recycling is ultimately a story of hope and human ingenuity. It demonstrates our ability to learn from past mistakes, to develop technologies that work in harmony with natural systems, and to create economic systems that reward sustainability rather than waste. Every recycled battery represents a small victory against the linear take-make-dispose model that has dominated industrial production for centuries. It's a step toward a circular economy where materials flow in closed loops, where waste becomes input, and where the true cost of our consumption is accounted for and minimized. As your old smartphone battery begins its recycling journey, it carries with it the potential to power future devices, to reduce environmental impact, and to contribute to a more sustainable world. The lithium that once traveled from Chile's desert, the cobalt that came from Congo's mines, and all the other materials that made your digital life possible will live on in new forms, serving new purposes, enabling new connections. This is the true secret life of your smartphone battery, not just its journey from raw materials to finished product, but its endless cycle of renewal and rebirth. In a world facing environmental challenges and resource constraints, this circular approach offers hope for a future where technology and sustainability can coexist. As our journey through the secret life of your smartphone battery comes to an end, take a moment to feel the weight of your phone in your hand. It's remarkable how something so small and light can carry such an enormous story that spans continents and centuries, that touches the lives of millions of people, and that reflects both the best and the most challenging aspects of human civilization. We've traveled together from the ancient salt flats of Chile, where flamingos dance beside evaporation ponds, and indigenous communities watch their world transform. We've witnessed the tragedy of children working in cobalt mines in the Democratic Republic of Congo, their childhoods sacrificed for the metals that power our digital lives. We've marveled at the precision and scale of Chinese manufacturing facilities where millions of battery cells are born each day. And we've glimpsed a future where solid-state batteries could revolutionize portable power. We've seen how recycling can transform electronic waste into valuable resources, creating circular systems that could sustain our technological civilization for generations to come. But perhaps the most important part of this story is the recognition that every technological choice we make has consequences that ripple across the world. The battery in your phone connects you not just to the global internet, but to a global web of human relationships, environmental impacts, and moral responsibilities. The lithium in your battery carries with it the dreams and struggles of the Likananti people, whose ancestral lands are being transformed by mining operations. The cobalt connects you to children like Montash and Faustin, whose lives have been shaped by poverty and the global demand for the metals that power our devices. The precision manufacturing connects you to millions of workers in Chinese factories, whose skill and dedication make our digital lives possible. This interconnectedness is both humbling and empowering. It reminds us that we are not isolated consumers, but participants in a global system that affects real people in real places. Our choices matter. The devices we buy, the companies we support, the way we use and dispose of our technology. The future of battery technology will be shaped by the values we choose to prioritize. If we demand longer battery life above all else, manufacturers will focus on energy, density, and performance. If we prioritize sustainability, they'll invest in recycling and renewable materials. If we insist on ethical supply chains, they'll work to eliminate child labor and environmental destruction. The solid-state batteries and advanced recycling systems we discussed are inevitable. They re the result of conscious choices by researchers, engineers, companies, and consumers who believe that technology can and should serve humanity's best interests. Every breakthrough represents thousands of hours of work by people who chose to dedicate their lives to solving these challenges. As you drift toward sleep, carrying with you the story of your smartphone battery, remember that this story is still being written. The next chapter will be shaped by the choices we make in the coming years, choices about what kind of technology we want to support, what kind of world we want to live in, and what kind of legacy we want to leave for future generations. The secret life of your smartphone battery is ultimately a story about human connection, our connection to the natural world that provides the materials for our technology, our connection to the people whose lives are affected by our choices, and our connection to future generations who will inherit the consequences of our decisions. Tonight, as you set your phone aside to charge, take a moment to appreciate the incredible journey that brought that small device into your life. From ancient geological processes that concentrated lithium in desert salt flats, to the ingenuity of scientists who unlocked the secrets of electrochemistry, to the dedication of workers who transform raw materials into sophisticated technology. Your phone represents the collective effort of countless people across space and time. But also remember the responsibility that comes with this knowledge. We who live in the digital age have the power to shape how technology develops, to demand better from the companies that serve us, and to use our devices in ways that honor the true cost of their creation. The story of your smartphone battery is a reminder that even the most mundane objects in our lives carry within them the entire history of human civilization, our triumphs and our failures, our ingenuity and our short-sightedness, our capacity for both creation and destruction. As you rest now, let this story settle gently in your mind. Let it remind you of your connection to the wider world, of your power to make choices that matter, and of the incredible privilege of living in an age where the accumulated knowledge and effort of millions of people can fit in the palm of your hand. The secret life of your smartphone battery is, in the end, a reflection of our own secret lives, complex, interconnected, full of both wonder and responsibility. May this knowledge guide you toward choices that honor both the remarkable achievements of human technology and the precious world that makes it all possible.